All right, so this is the third video of the day. Um, this is going to be for question B2. So it's not any of the prompts, it's one of the questions in the post lab. It asks, compare the theoretical and experimental observed buffer capacities for your histidine buffer at pH 6.0. So what I'm not going to do is go through this question and basically give you the answer because everyone's going to end up with the same exact answer. So what I'm going to do is I'm going to go through, using the data that we have. But what I'll do instead is I'm going to solve for a different um, buffer capacity at a different pH. So let me just turn this question around and save another another thing here. So what I'm gonna basically change this question is, what is the buffer capacity, the theoretical and also experimental buffer capacity at, let's say, pH 9.5. Okay, so how would I go about this with the data that I have? Well, the theoretical buffer capacity can be um, calculated based off of the information that we know and also the Henderson-Hasselbalch equation. So let's go ahead and solve first for the theoretical buffer capacity of this histidine buffer at pH 9.5. So what we first need to do is revisit the Henderson-Hasselbalch equation, which states that the pH of a solution is equal to the pKa of the functional group that you're observing, plus the log of the conjugate base concentration over the concentration of the acid species. Now, for the remainder of the work, I'm not going to be putting all the, yeah, never mind. I'll stick to proper notation for concentration. So we already know what the pH of the solution is for this particular question. It's 9.5. Again, you're asked to solve the buffer capacity theoretical and experimental at 6.0. I am going to give you this example in terms of the pH of 9.5. Now, the functional group that is relevant at this pH is the functional group for the amino group. And that one has a pKa in the lab manual at 20 degrees Celsius for the charge 0, the Z charge of 0, being 9.33, and then plus the log of the concentration of the conjugate base over the concentration of the acid species. The reason why we are trying to solve for the concentrations of the acids and bases is because the second half, or another equation for buffer capacity, basically allows you just to simply input the concentrations of these conjugate base and also acid species. So if we know those, we can plug those into the second part of the buffer capacity equation. Then what we're going to do is just solve this as best as we can, subtract 9.33 from both sides, and we end up getting 0.17 on the left side, and then equal to log of the conjugate base. That's really bad. Over the concentration of the acid species. And then what we can do is take both sides, base 10, and this will give us 10 to the 0.17 equals to, and then base 10 of log base 10 will pretty much cancel that whole thing out, and all we'll end up getting is the ratio of the conjugate base over the acid species, and 10 to the 0.17 is equal to 1.479. So this is the ratio between the conjugate base and the acid species. The ratio is 1.479, but we need an extra amount of information here to finish solving this problem. And this has to do with the concentration of the buffer that you made and the I wouldn't want to say the equilibrium, but the sum of the conjugate base and acid species, the protonated species, being equal to the concentration of the buffer they created, because mass isn't created nor destroyed during this experiment. And the sum of the buffer in its conjugate base species and acid species should equal the concentration that you prepared. Many of you are going to think to yourselves, oh, well, I know how much buffer I made. I made like 0.4 molar histidine hydrochloride buffer. Yes and no. Yes, because that is how much we asked. That's the concentration of the buffer we asked to prepare. No, because that's not what you did your experiments off of. If you remember the procedure correctly, you were asked to make 75 milliliters of this 0.4 molar histidine hydrochloride buffer solution. But when you actually did your titrations, you only took 25 mil aliquot of that buffer, and then added an equal volume of deionized water. So you actually weren't titrating 0.4 molar histidine hydrochloride. You're actually titrating 0.2 molar histidine hydrochloride that entire time. And if that's the case, let me see if I could start deleting some of the, start erasing some of the things that I wrote up here. So I can get rid of the Henderson-Hasselbalch. This is pretty cool. And we still want to keep that ratio down there, so I'll make sure I don't delete that bit. Then what we can say based off of that observation that we made, that we were titrating the entire time 0.2 molar histidine hydrochloride solution, is that the concentration of the, let me just keep everything in the same color so everyone can follow along. The concentration of the conjugate base species plus the concentration of the acid species in solution should always equal to 0.2 molar. We're just changing the protonation states of the buffer at different pHs. We're not actually, synthesizing or destroying anything. So with this, we have two equations, both with two variables. We can start solving for both variables here. And we can say that the concentration of the, how do I want to do this? Yeah, let's say that the constant, in this first equation, let's subtract HA from both sides. And what we end up having is the concentration of the conjugate base is equal to 2.2 molar minus the concentration of the acid. So what I'm going to do now is take, every time I see the conjugate base concentration in the ratio equation that we solved earlier, I will substitute in 0.2 molar minus concentration of the acid. So that is now going to give me, I'll start up here, 0.2 molar minus the concentration of the acid divided by concentration of the acid equals this ratio of 1.479. But whenever I see these types of equations, I just, that ratio, I'll just simply divide it by 1, and then I can just do a simple cross multiplication to straighten everything out. And the equation that I get is 0.2 minus concentration of the acid. Please forgive me. I left my nice stylus at work. Equals, and now I'll resolve the cross multiplication for the other numerator and denominator. 1.479 times conjugate, or sorry, concentration of the acid. I'm going to go ahead and add acid concentration to both sides. And what I end up getting is 0.2 equals 2.479 conjugate acid, or sorry, I keep on saying conjugate. 0.2 equals 0.2479 times concentration of the acid. Now, what I don't need anymore is this. Keep that bottom part. Actually, I'll also erase that. And I'll get rid of this here. And then this will give me concentration of the acid when I solve for this variable. It is 0.0807 molar. This leaves me for a conjugate base concentration. Remember, the sum of these two have to equal 0.2 molar. Therefore, the concentration of the conjugate base species needs to be 0.1193 when I solve for this. Now, just looking at these two concentrations, remember that I said the pK of the amino group is 9.33, but I'm asking for the pH at 9.5, meaning we're higher than the pK. The pH of the environment is higher than the pKa, meaning that functional group will be more deprotonated than protonated. So do these concentrations that we solved make sense? Let's just give a quick look. Yes, they do. The concentration of the conjugate base is slightly higher than the concentration of the acid. That's because the environment is going to confer more of the deprotonated species to be in solution compared to the protonated species. So from here, now we know that these two concentrations, we can go back to the buffer capacity equation. And that is going to be buffer capacity equals the negative differential of the proton, millimoles of the proton solution over the differential of the pH, or simply we'll just use this other equation now that we know the concentrations of these two species. It's 2.303. I'm running out of space here, so I'll go ahead and start to erase some things that are not needed anymore, times the product of the acid and conjugate base concentrations divided by the sum of the concentrations of the acid and the conjugate base. And when we do this, we get 2.303, and in the numerator, what did I have written here? We get 0.009628, and the denominator we get 0.2. Does that make sense? Yes, it does make sense, because remember, in the denominator, that was supposed to be the sum of the acid and conjugate base species, which we already said earlier should equal 0.2 molar, because that was the concentration of buffer that we had. So this is just also a nice little check here that we're not, fudging the numbers or messing anything up. And then that, when we resolve this equals this whole buffer capacity calculated value is equal to 0.111 molar per pH. Now we take a look at this. At pH 9.5, for this histidine hydrochloride solution, it's going to take 0.11 molar, a change of 0.11 molar of either acid or base to change the pH by 1. Those would be the units for buffer capacity. So remember when I said earlier in the discussion slides for chapter 2, the higher the buffer capacity value, the more resistant there is to the change in pH, because basically for the units here, what it's telling you is you'll need more concentration, you'll need a higher concentration of the titrant to change the pH, to change it to by 1 unit pH. So in this case, at pH of 9.5, we'll need a change of 0.111 molar of the titrant in the solution to change the pH by 1. So that's essentially the theoretical value that we get at pH 9.5 for the histidine hydrochloride solution. How do we find our experimental values? All right, well, there's 2 ways of doing this. One way is pretty straightforward and easy. The other one, I really don't recommend it unless you have like an extra 30 minutes of time that you don't mind spending, but it does take a little bit of time. So we need to revisit our data. If I could manage to, oh, I can just start sharing the other screen. So when we revisit our data, again, this question was the buffer capacity, experimental buffer capacity at 9.5. That's what I'm asking for in this example. We can take a look at this data that we had here earlier and see what values do we use from our data to find the buffer capacity. Can I annotate this? I should be able to. Here we go. Okay, so no color red. Okay, I'm just gonna find some white space really quickly here. So let's say again what the buffer capacity equation is. Buffer capacity equals the negative differential of the millimoles of protons in solution divided by the differential of the pH of the solution. Now, the second way to solve for the experimental buffer capacity, you can actually calculate the slope of your titration curve. Take the inverse of that, and you'll be able to find the buffer capacity. But these equations are not easily, you cannot model them very easy, and you cannot get nice equations like y equals, ax squared plus bx plus c, find the derivative for that, and then you'll be able to find the slope of your curve. So what we can do is kind of like this poor man's approximation, just by slightly modifying this equation a little bit. We'll still have the negative sign in the beginning, but instead of the differential of the protons in solution, the millimoles of the protons in solution, we'll just say the change of the protons in solution divided by the change of the pH. And of course, we're going to do this surrounding at a pH of like 9.5. So what we're going to do is, if you look back just right behind all of these equations on the data back here, I've highlighted 3 sets of data, one at pH 9.25, one at pH 9.5, and one at pH 9.75. So we're going to approximate around pH 9.5, meaning we need our pH 9.25 data, and we also need our pH 9.75 data. And we can kind of basically, if I'm just gonna move, I'll just draw it here. If we have our titration curve, and this is pH 9.5, and then 9.25 is over here, and 9.75 is over here, we can basically use this poor man's approximation and find the slope between these 2 points around 9.5 and get an approximation of what the buffer capacity is. So let's just go ahead and do that. So let me see. I want to only keep, I'll just erase everything else. Okay, I'll make it fit. Okay, so we need to identify in this the slope that we're going to be using around pH 9.5. I will move a little bit further down. Okay, great, perfect. And let's say that we're traveling in our titration curve from left to right. If we're traveling from left to right, our pH values are going from lowest to highest. So if we're going from lowest to highest, then here in pH 9.25, this will be our, I'm not writing, oh, there we go, pen. This one will be our initial value, and 9.75 will be our final value if we're traveling the titration curve from left to right to get that slope. So now to get the buffer capacity, the experimental buffer capacity based off of this like kind of approximation method, what we're going to do is then substitute the deltas for the final and initial values. So again, we're going to end up with negative, and then the concentration, or not the concentration, sorry, this is millimoles of titrant of the protons final minus the millimoles of the proton, acidic protons initial, divided by the final pH minus the initial pH. So where do we get these values from? Of course, we're going to get them from our data. The millimoles of proton final is going to be 17.865. Oh, I'm forgetting that there was a negative sign back there. 17.865 minus 14.187. And then divided by the pH final, which is 9.75 minus 9.25. Now there's an issue with this. Those titrant values that I just copied from my data, they are not the titrant values for the acid, they're the titrant values for the base. So how do we turn bases into acids? We simply just basically take the opposite, the negative sign of those. So what we have to do now is add, it's going to be negative 17.865 and negative 14.187 there. So when we resolve that in the numerator, what we should end up getting here, let me see my notes. We will end up getting negative for the whole answer equals negative, and then the numerator will be negative 3.678. That's what you get. Negative 3.678 is what you get when you take negative 17.865 and subtract negative 14.187. And then in the denominator, we're going to resolve 9.75 minus 9.25, which is just going to be 0.5. And when we solve for this, the negative in the numerator of the fraction times the negative sign right before the fraction is going to cancel out. So our answer is going to be positive. That's great. 3.678 divided by 0.5 is going to be 7.356. But what's our units? Our units in the numerator are the millimoles of the acid titrant, And in the denominator, it's pH. So we're not really getting the same units that we had for buffer capacity when we use the equation, putting in all the concentrations of the acids and the conjugate bases. And that's because the theoretical equation that we worked with, that all had concentrations in it. Concentration squared in molar in the numerator, and then concentration in molar in the denominator, which ends up giving you concentration in molar per pH unit. Here we only have millimoles of the acidic titrant. So we're missing a dimension to get to molarity. We're missing the volume dimension. So at this point in the titration curve, in my titration curve, you know, around 9.5, I had already added 16.076 millimoles of titrant. I'm going to go ahead and start erasing some stuff from here. And I think, yeah, I'll just go ahead and just start deleting these things here. I started off, remember, with 50 milliliters of buffer. And then at this point, to get to around pH 9.5, I already added 16.076 millimoles of the 0.5 normal potassium hydroxide titrant. I need to know how much additional volume I had added at this point. So if we know that 0.5 normal titrant, which is the same as millimoles per milliliter, times some volume is going to give you the millimoles of titrant. If we already have the millimoles of titrant, dividing by 0.5 is going to give us the volume. So let's go ahead and do that. Let's see what volume, you know, if you already have the volumes for this pH point, you can just go ahead and refer to that in your data set. But I'm just going to show you how to do this backwards. The millimoles of the titrant, 16.076 divided by 0.5 is equal to approximately 32 milliliters. And that should agree with the data that I had before. And we can just kind of check it really quickly just to make sure that that was the case. It was the potassium hydroxide at around 9.5-ish. Yep, there it is. 9.47 pH was approximately 32 mils of the titrant. So the math checks out. And then now I will, oh, perfect. I'm back in line. This is good. So 50 mils of the starting solution plus 32 mils of the amount of titrant I had to get to this point is going to give me a total volume of solution of 82 milliliters. And this is that volume dimension that we were missing from our answer that we had just calculated before. So again, give me 1 second to just kind of start erasing things so that I can fit more information here and start writing things out much better. So 7.356 millimole of the acidic titrant divided by pH, then divided by 82, or sorry, I said acidic, millimoles of the acidic titrant divided by pH. No, it should be per pH. Divided by 82 milliliters, we got millimoles in the numerator and milliliters in the denominator. The millis will cancel out. We got moles over liters, which gives us the units for molar. And then, of course, the acidic proton just stays there. Moles of the acidic proton per pH unit. And then 7.856 divided by 82 mils gives me 0.0897, approximately 0.09 moles of the titrant per pH. This answer that I end up getting, again, says the exact same thing for buffer capacity, except we, oops, here. It says the exact same thing for buffer capacity as the last theoretical calculation that we did, except this one's a little lower. If you remember, if you kind of scroll back, the buffer capacity that we had calculated theoretically was 0.111 molar of titrant per pH unit. Here we're calculating about 0.09 molar titrant per pH unit. It's just kind of saying the exact same thing in that this is how much we need to change the concentration of the titrant by to change the pH by 1 unit. And these are actually pretty close estimations to the theoretical buffer capacity. They're in agreement with one another. And so this is pretty good. The other way that we can do this, and again, this is kind of like being a little bit more thorough, but you need a little bit more time to do this. I'm going to clear all, oh, cleared everything, great. If we had the time, if we had the resources, we could model this titration curve to get an equation. And again, I'm not going to model the whole equation. That would be really hard. Plus, also, our data is not the greatest. But I can just take this surrounding data here, graph it, and then using a trend line, and again, Excel is not really the best way to do this because it's powers for fitting curves into the data, and it's, regression analysis is probably not the best compared to other software suites like MATLAB and Prism and so on and so forth. But if we can do this, then what we can do is get the instantaneous change at a certain value, like 9.5. If we have the fitted equation, we can find the derivative, the first derivative of that equation, and then figure out what we end up getting. And I kind of like played around with this a little bit on Desmos's graphing calculator. And the titrant, if you remember, the titrant value that I was at was about 16, what was that again? 16.076 millimoles of the acidic titrant, so 16.076 right here. That first derivative value at that titrant is going to be, the slope is going to be 0.15558. That is the slope for this. And what we have to do is, if you take the direct slope from those titration curves, the slope, if you remember, I'm actually going to draw this a little backwards. If this is slope, pH is on the y-axis, acid titrant millimoles are on the y-axis. Slope is always like the rise over the run, meaning this is going to be the change in the pH over the change in the acidic titrant. And that's actually not the same as what the buffering capacity equation was, which is the differential of the proton concentration over the differential of the pH. And so if we wanted to use the slope, the first derivative off of the first derivative of the equation that we modeled, we'd actually have to take the inverse of that value that we just seen. So we have to take the inverse of 0.15558. So if slope equals 0.15558, then the inverse of the slope, God, this is terrible handwriting, inverse of the slope equals, and I wrote this out somewhere possibly? No, I didn't. So I'll have to drag my calculator in the view now. 0.15558. Take the inverse of that, and that is going to be 6.428. Change in the proton, millimoles of the proton per pH. Again, we're missing this component of the volume to get a molar over pH, but the volume that we had solved previously should be the same for this, so we can just divide this new number by 82 milliliters. And when we go ahead and do that on our calculator, we actually get a number that's a lot less than either the theoretical or the experimental buffer capacity that we had calculated earlier. We get a like instantaneous buffer capacity based off of the this kind of like modeling first derivative method of 0.078 per molar of the acidic titrant per pH. And that's that. You know what? I kind of just basically really, you know, the data that we have is not that great. Plus, also the modeling curve is not the best. So this one, I would expect it to be pretty different and far off from the other two. But you now have the tools that you need to calculate the theoretical buffer capacity at pH 6.0, and also using your data, calculate the experimental buffer capacity at 6.0 using that, you know, pH approximation method that I had showed in the middle of the video. This last one, again, you know, only for if you want to do it for kicks, go for it. Or if you want to really learn how to figure this out at some point, you know, if you're super interested, meet me in office hours. I'd be more than happy to you know, guide you through that third calculation